Hey, Rajat, how are you? How are you, my brother? Very good. And Deliran joined too. So another brother. He doesn't know how to. Okay, so people are going to keep joining. Avishai, thank you for joining.
Hi.
Hi. So I really want it to be interactive, but it's going to be very deep and it's going to be very, very. You can't understand most of the topics. I'm not going to derive any equation that I'm going to talk about, but you're going to understand the essence behind the topic called turbulence, besides when it initiates and when it, laminarity is bad. So actually understand the topic of turbulence. So what you see on your screen is supposed to be like my blog, right?
Yep.
It's the blog?
Yes.
Yes.
Great. I really did some changes to my blog lately. I'm not such a good visualizer and creative person when it regards to, being an artist. My mom is, though. Everybody who read some of my blogs saw that she painted me Starry Night. Here it is. That's a Starry Night by my mother. Nice. Can you see it?
Yep. Very nice.
Yeah. Okay. So my blog is now such that you have, maybe I'll put less posts here because it's getting really long. And then you have here a part of this changes all the time, top posts and pages according to the statistics. So you can see which kind of, but this depends mostly of what I, publish, not about. But some are here all the time, like understanding the business hypothesis is all the time. It's a must. Numerical schemes in CFD is a real must. Someone who wants to understand this was like a flow of craziness. I just started to write about discretizations and the Reynolds cell problem. If someone doesn't know what I'm talking about, you can say it's okay. And I found myself after 6,000 words trying to cut it. Recommended books. It's really cool books, but then I can give you 100 others. There's an index. It's a sticky page. You can get inside the index, and we'll do that. And then you can find all the posts. Recently, as you see, the blog is not owned only by me. It's owned also by Alon Davidi. I don't know if most of you know him, but he's a genius. I mean, he's kind of dealing with chemical reactions and fire safety and topics which are really exotic and machine learning. So he didn't contribute yet so much, but he will, hopefully. Otherwise, it'll kick his ass. And again, you can navigate here, go to see every inch. I mean, there's lots of slide shares. Most of the slide shares have links to the posts or to other resources, which I think they are good. Tips, I'm going to start giving a lot more tips. I want to let you know it's a due diligence. I'm now in a contract with the company that sold. Most of you know me as the Tensor guy, the ANSYS guy. So I started to work with the company that actually distributes Star CCM. But it's not going to influence the fact that I've been with Fluent model analysis. There are some documents in Hebrew for those who are English challenged, and some of them are not also in English. You don't have them in English. A full course of CFD from Sami Shamoun, The Law of the Wall in Hebrew, a few aspects of Franzen's growth. It's a 52. It's my thesis, like notes, and some other stuff. These two, if any one of you wants to learn large eddy simulation, these are your links. They're here. Open them. You really can start simulating without a lot. One of them is Mentes. The other one is Alexei Gerasimov, the kind of opponent, in ANSYS. So I put here a lot of movies that I find beautiful. Each one of them is really worthwhile. This is a combustion course of Professor Heinz Pitch, which is a world-renowned individual in the field. He gave it at the US, and it in the minimum, my post, the minimum something to be a CFD practitioner. It appears there, but you can also reach it from here. This is an amazing article from Madeleine. She's a senior lecturer, Madeleine Combry. She's a senior lecturer I met in LinkedIn, and she simply wrote an article which I hope someday I could reach just the level of writing. And amazing. Now here are advices. Use them. Okay, you want to learn CFD? Use them. First of all, go to Lorna Baba open YouTube videos. There's one of learning Python, 12 steps to Navier-Stokes, but you start with this one, computational fluid dynamics. There's no touching Fluent there. Fluent is not a CFD software. It's just a platform, a GUI. Knowing how to push buttons doesn't do much. These are some recommended, highly recommended links. I think that if you walk through them, you have all you need to know about, with the addition of the Feynman lectures, of Caltech actually advertised all of them, and then you can know all of physics, except some of the stuff that is today. Contributors, of course, Joseph Moran, most of you know him, very active. Some of them I like, some of them I like less. I can tell you I worked a lot for ANSYS, for the ANSYS channel partner, Intenza. I specifically never liked the company. I think they did, especially in my field of fluid dynamics, lots of mistakes, especially with the meshing, and I don't really am fond of the company. Siemens bought now Star CCM, so there's those two top-notch softwares. Siemens also combines the world of experimental physics. Okay, they kind of got really in charge of doing the whole way, the V&V plus doing the part of the simulation. I want you to remember there's a trend going on, and the vendors are trying to sell you this trend with beautiful pictures. Simulation, simulation, simulation. No, it's not about simulation. If you don't understand what you did in any of the steps that you did, you can't have a V and V, and if you can't have a V and V, then you didn't produce a simulation. You produced a GIGO. Okay, so Joseph Murad, follow him, man. He's everywhere. I wrote Engineering Mind, but there's a YouTube channel. There's a SceneScale stuff. It's not SceneScale blog, but I can't write Joseph Murad all over here, so I didn't. Leap Australia has a wonderful ANSYS blog. If you want to learn like stuff to do actually, like tutorials, go there. Resolved Analytics is a good company, but they don't change the blog much. Then, of course, CFD Online. I think CFD Online is a little bit of kind of reminds me an analogy to OpenFOAM. It became kind of a mess of different questions, different topics, different, even the main forum. And of course, mostly highly recommended, my friend Tobias, which opened his. He actually worked years and years to get to this level of. It's not the site; it's finishing his doctoral dissertation, and this is OpenFOAM. This is an OpenFOAM contributor, like. Almost none other. So if some of you want to use OpenFOAM, for me, OpenFOAM, I love OpenFOAM. I'm going to go back and use it, but it's like an ocean. I mean, it's really hard to get around, and you need to be very good. So visit the site. Upcoming webinars, not important. Hiring position, I put some, mostly for the Israeli guys, and courses. Okay, about courses, I've decided there is some courses that you can get in touch with me privately and we'll settle them, but then you'll have to learn by yourself. I've decided it's the first time I monetized the site by some way, and it's private mentoring. I get like, especially when COVID started and the Zoom lessons, I get over 30 students. I mean, not over 30 weekly, but I get like a bunch of students weekly, 10, 15 students who ask for help and seem to not have learned anything about CFD. And I find it. I spoke to the CFD lab professors. I'm in touch with each and every one of them, and they told me, undergraduates don't come to lectures, stuff like that. But I've decided to start with some private mentoring. I think I'm very modest with my fee. I mean, getting 5 hourly sessions for $50 is a joke. Those of you who talk with me on the phone know that I give much more than. I mean, what's written here. You talked about David E. Wilcox. Every reference reminded here, maybe, but that's off the record. Maybe deliver to you. Just ask, okay? You don't need to mute yourself. I want it to be interactive. So unless you're going to scream like a crazy person, you can unmute yourself. Or you have a dog which, I don't know, likes to bark every time he hears me. This is a picture of me. It's kind of the best picture I have ever made, because I'm not photogenic, but that's a big part of my life. I'm like a Judaist, Mahayana Judaist, doing 2 hours of meditation daily and really focusing on mindfulness, stuff like that. So that's about the size. Now, gonna go on, okay?
Okay.
We're going to start our modeling transition. Yusha. Modeling transition. I made a post about modeling transition. It has many short explanations of but what we're going to start with is going to be a little bit of background about transition. We're not going to talk too much about visualization of transition because I think it's too hard to explain large eddy simulations and DNS over. Maybe we're going to have another session dedicated to it. Okay? So, you ready?
Yes, sir.
Yes, sir.
Very cool. Very, 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 very cool. So, transition. What comes into mind to many of you? Someone throw stuff in the like unmute yourself and it's interactive. I'm going to talk a lot. I can talk like people know me. I can never stop talking. Is it a number? Is it a guy? Is it what? A laminar flow is usually can be described as a 2D flow of laminas. That's why it's called laminar flow. And you know about turbulent flow that you can't really define it, but it's a chaotic, seemingly randomly flow. That's you have Mattia can join. I'm really not paying attention to this. I need someone to look at all the stuff that is going around because people are waiting for no reason. So what comes? Is there something comes to mind for him? It can be a simple thing. You shouldn't be ashamed. You don't have to know everything. Yeah, exactly. We have a laminar flow. We usually can describe it in 2D. And then, like in life, there's always some kind of disturbance. And mathematically, the Navier-Stokes starts to, because it's a nonlinear equation, a very nonlinear equation of a certain type, starts to have branches of solutions, which are all of them, legit, depending on what you want to call legit. They don't exist, some of them, but they are legit, but some of them are unstable. So taking a flow, which is laminar 2D, and destabilizing it. So the behavior and properties of fluid flows is important in many technical applications. I mean, laminar flow is well predictable, it's structured, it's layered, it's, from the Latin word lamina, layer, sheet. It usually exercises significantly less frictional resistance. So solid bodies, it has much lower mixing. Everybody who knows, who practices thermal analysis knows that one of the advantages of turbulent flow is the mixing. So rather lower mixing rates than the chaotic swirly and dictating both flow of turbulent and laminar flow. And there's a crucial variety of technical applications where, like boundary layers on aircraft wings, around cars, now especially with green energy, and besides that, it's a topic which I find amazing. It's turbine blades, because it also involves two things: a high of turbulence intensity, both high turbulence intensity and both low Reynolds. So if we have a really high Reynolds, probably soon enough the flow would be turbulent. But turbine blades enjoy lying most of the time in the world of transition. And of course, flows of chemical reactor, combustion engines, the evolution of initial laminar flow into a fully developed turbulent flow is called laminar turbulent transition. The mechanism triggering this transition are not fully understood even today. So I'm going to go to three outlines of which kind of transition descriptions there are, but then I'm going to go to the important one, which is mine from the 52 pages of summing all the stuff up. So everybody wants his own transition mechanism to be very important. There have been fights. I'm going to introduce you a big fight about transition mechanisms. And it's about a century of research, but a little bit more. It's like a century and a half of research of transition, and it's still not well understood today. I'm sharing the screen. The what do you see? You see my blog. You see here, right? That's what you see. The bypass transition. These beautiful pictures. Transition mechanisms. Someone say yes or no. Do you have a black screen? Okay, so which kind of dimensionless number comes to mind when we're talking about transition?
Reynolds number, as in.
Someone say clearly Reynolds.
Yeah.
Yeah, and notwithstanding what you have been taught in the university, it's not the inertial forces. It's not the ratio between the inertial forces to the viscous forces. That would be very stupid to say, but a good description of a good and easy description. We can say the means by which cross-rim momentum is diffused across the boundary layer. But this would be more sophisticated, like smart. We can say it's the thickness of the boundary layer. The thicker the boundary layer, the lower the Reynolds. That's it. So a Reynolds is a measure of the thickness of the boundary layer. So, as I said, laminar flow remains a solution of Navier-Stokes. That's true. That's totally true. There's nothing to it. But then because of a disturbance, it becomes unstable. So we can have many kinds of disturbances. We usually, when we come to explore something, why is it so hot in the room? I don't know, because the air conditioning doesn't work. Shit. Oh, it does. Probably anxious. Again, the critical non-dimensional parameter is the Reynolds number, which you mostly learned as defined as the ratio to inertial to viscous forces. But working on a circular cross section, but but it's not. It's what I said. And there have been found precise values depending mainly on the level of disturbances at the inlet and the wall roughness, of course, which introduces disturbances in the pipe. Reynolds number of particular important flows are known. They can be even high as millions and billions. They can be a few thousand, depending if it's a closed flow or a boundary layer. If it's a curved boundary layer. The behavior is generic. Although the laminar flow remains a solution of the governing equations at all Reynolds numbers, okay, so it's a solution. It's not that you don't have a solution anymore. If you did the DNS with like taking Fluent and doing a laminar flow simulation, but not using the second order upwind by using a high order, you probably wouldn't be you wouldn't be able to get the laminar solution. It would be unstable and chaotic. Okay, so the history of transition, of course, goes back to the classical experiment, which you can still find in I think, the London Imperial College of London. The experiments by Osborne Reynolds. He injected ink into a glass tube. He discovered that the change from laminar flow to turbulent flow is basically dependent on the Reynolds number, and this number depends on the velocity, if it's a pipe, then on some length scale, and the viscosity. This is a huge step in fluid dynamics, which can never be understated. So that's why Osborne Reynolds is considered and shall be considered so renowned for his. But specifically, the experiments he made showed something about transition. You all know Moody charts. I hope so. You met them at the undergraduate studies, and it seemed to depend on many things why certain turbulent flow becomes stable or unstable. So what we do usually in our field called mechanical engineering or dynamic engineering, we have the engineers, we have the physicists, we have the engineers. We make solutions out of good and solid phenomenology. We have the physicists who understands the phenomenology, and then we have the breakthrough guys, which are mathematicians. So without mathematicians, there would be no breakthrough. There would be just phenomenology not clearly understood. So later on, in the beginning of the 20th century, both Orr and Sommerfeld, very important name, independently, like Navier and Stokes independently did, derived the linearized stability equations. What means linearized stability equations? It means that we take the Navier-Stokes equations, we linearize them, we add a perturbation, and then we have an eigenvalue problem. So that's as far as I'm going to get inside I'm not going to derive you now Orr-Sommerfeld equations, but I am going to share the screen and show that if we look, I think I have them here. Orr-Sommerfeld equation. In addition to it, there's the Squire equation, which works on one of them works on the say velocity vector. This one is the vorticity vector. and it's going to be very important to mechanisms of transition, because most of the work done lately has had used the result, the aid of vorticity, which is actually just the curl, the velocity, to explain mechanisms of transition. So here you see the stability equations. Stability equations means solving an eigenvalue problems. You get an eigenvalue, you have an eigenvalue, and you have an eigenvector, and then you can say, and if it's a kind of equation which the result is exponential growth or damping. I mean, you can say there's a growth, there's a damping, there's a growth. You can draw your branches. If it breaches this branch, then it becomes growth, and the disturbance grows. And until when does it grow? It grows enough. We start with an infinitesimal, because it's a laminar flow, and we can't laminarize without an infinitesimal disturbance. And then when we get to the stage where the disturbance is high enough, then we cannot say that nonlinearity is negligible. And then we get to other types of growth mechanism. An interesting thing, a very, 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 very interesting thing, is that it was proven that it's called the Reynolds-Orr equation. And in the Reynolds-Orr equation, what I will not, of course, develop it, but it's usually writing the kinetic energy and see how it changes on time. And I mean, by time, okay, of a laminar flow with a disturbance. Okay, you with me? Has proven that the only mechanism of growth possible is a linear mechanism. I mean, so what we have here is a linear growth. It could be a modal growth. Okay, the Orr-Sommerfeld equation has eigenvalues. There could be an orthogonal basis, right? We learned that together at Algebra 1, an orthogonal basis. And then this orthogonal basis has some modes, some eigenvalues, which are most susceptible to have the greatest growth, let's say. So if I draw some kind of line, if I do a continuous investigation, or if I do a discrete, I take 6 points, then there's some kind of line of which one eigenvalue goes through the line and growth happens. Okay? So one type of transition we have, which is really very known, is the modal transition. Most of you know it. It was found after some investigation of Turbine and Schlichting, and was verified by Turbine and Schlichting also. And it's a Turbine-Schlichting wave disturbances in a flat plate boundary layer, but also on an airplane wing, which means very low turbulence intensity. One mode we conduct a stability analysis, okay? we find one mode, which in this mode the flow becomes unstable first. So it could be Turbine waves for boundary layer, but the late Orsag, I hope many of you heard this name. The late Orsag found the number 5772 as the Reynolds number for an eigenvalue that gives you the shift to turbulence in quiet flow. Okay, so there are many. So there are many kinds of different transition. What actually most did is introduction breakthroughs by changing the intensity of the turbulence in the inlet, maybe introducing secondary instability. Maybe introducing this second instability after the laminar flow becomes disturbed. It's no longer 2D flow. It's like 3D flow and distorted one. So maybe introducing another secondary instability theory to investigate the now, instead of the laminar flow, the disturbed flow. So that's where the secondary instability theory comes from. And when they did that, the classical mechanism of the disturbance of modal instability solutions, which you see here, okay? These are the Klebanov and Haber type. They look somewhat the same, maybe to some of you, but they are really not. Maybe I can give you a better picture of it, and then I will give you a better picture of it. Maybe this one would be a lot better. No, it's the same. It's the same picture. It's a subversion picture. Here you see the 2-inch the modal stability analysis solution for transition. The only one which is modeled, the Turbine waves. We get very stable laminar flow with very low intensity of turbulence. And then at the critical number, we start to get elongated and non-elongated streaks, which turns to turbulent spots. And that's probably what you about of transition. Then most of the work was done by DNS and LESS, because it's very hard to work with PIV to check this kind of flow structures. And most of the work was also to find which kind of structures we have there. Are there gamma-shaped vortices? Are there hairpin vortices? It's very important to show, probably if you're doing some kind of research, to show that you have discovered a new mechanism of transition. Lately, Henningsen described the oblique wave transition and the transient growth transition. and we're going to start talking about that. So, a few aspects about turbulence. The beginning of explanation. Someone wants to ask a question. Did someone not understand anything? We have 45 minutes. It's a lot of time to work on what we're going to do. You're not going to understand everything, I promise you, but you're going to get a sense of how this world of transition research works. Does anyone?
One question.
You always have to introduce yourself. Yeah, I know because they recognize you. But
so I just want to know if CFD tool can be can predict the transition.
That's part of what we're talking about. There's two parts of what you call predicting transition. There's a part of predicting transition onset, and as we said, taking like the OSAG 5772 solution to channel flow, and then doing an experimentation and finding out that the critical Reynolds number is actually 1,000, but stability analysis gave us something else. Okay, so that's one thing. That's like exploring the mechanism. Why does it happen? And to do that in a CFD software, by that you mean probably either OpenFOAM, if you're going to do it alone. I don't recommend, and I mean, if you're not part of KTA, which has an amazing DNS code, which you can download if you ask them. I mean, I don't recommend trying to do this on your own because it's too much work on it, on the side stuff. But if you decide to use Fluent, then there are models who claim to be able to cover a range of transition mechanisms depending on the turbulence. But you know, when you are acquainted with Fluent?
Yes, I know.
You are acquainted with Fluent? You know, you open Fluent GUI?
Sorry, I didn't hear you.
Did you open the Fluent GUI?
Yes, of course, yes.
Yeah. So you know you have to define if you define a turbulent model like a two equation to like okay, let's go straight to the point, like the LCTM transition model. Okay?
Okay.
Which has 4 equations, and it's actually this screen I'm sharing with you, right?
Okay.
Right? It's the screen I'm sharing with you.
Yes.
It's my wait a second. It's this. Okay. Now most of this post speaks about how we can predict transition with runs modeling. Volker from General Electric and Landahl and Menta, all of them really known collaborators. They actually for a type of transition for turbo machinery in E. I'm actually doing now. I'm starting a project with GE, so maybe I'll have the chance to meet this guy. It doesn't matter. You read it afterwards, enjoy it. It's correct. I promise you. The thing is that it claims to, no matter what mechanism it is, depending on the fact that you have 4 equation here, but it's actually a 2 equation plus the equations for the transition, like K omega and the transition equations. Okay. You always enter in the boundary conditions, a length scale and a turbulent intensity, right?
Yes.
So this model claims to by these simple and very non-describable, non-able to describe mechanism to predict transition onset and transition and laminarization. Okay? Point and point.
Okay.
So, but this is totally different than what I'm going to talk about. This is just predicting when transition starts and when transition ends. There was a method before that to do that. That's the EN method. What they used to do is do a kind of, I don't know if I wrote you about the method, but the EN method were, yeah, I did. The EN method, read it. And what they did is took a boundary layer code, a very good, very resourceful boundary layer code, matched it with an Euler code where the viscosity is not important, and then try to predict a kind of transition which is very modal. It's the Turbine one. Okay? So they get the spatial frequency of the transition, then they know the amplification, they know how much it grows. Very easy, but that's not what we want to talk about. Turbine waves are the fact is taking a laminar flow, taking an infinitesimal disturbance, superimposing it, solving the Navier-Stokes stability equations, and get orthogonal modes, which might, one of them or two of them have, especially the one with the biggest growth, would lead to the transition. But eventually, it's not what we see in nature. Okay? And that's an important thing to say. The initial start of the actually when at the same time, even before the same time that Osborne did his experiment, if you want the reference, you'll see it in the video. The basis of the explanation is going to be based on Ellingson and Palm. It's a 1974 paper, but it's a little bit different for practical reasons, so you'll understand it. A guy named Riley in the year 1880 showed that an essential condition for an instability of an inviscid flow, inviscid, meaning Reynolds goes to infinity, okay, is what is called an inflectional point in the profile. So where do we have an inflection point? We might have, we might create such a flow, but it's an essential. This criterion got a little bit pinpointed by a guy named Fj'ortof, and what I'm saying now is the most important stuff about the understanding of the phenomenology of turbulence. Inviscid instability is considered to be a very violent instability. Someone can give an example of such instability?
What do you mean about violent stability?
It's very violent. It's exploding, like Kelvin Helmholtz instability. Okay, so Fj'ortof showed that beyond this inflection point means that the second derivative of the velocity is zero. If someone doesn't understand it, it's important that you do. Okay, it means that the profile looks like I don't know, the second derivative is zero. To show you an inflection point now, I don't know how to find. Google it. You should know that. He showed beyond that, you have to have a maximum to the basic vorticity. It's like saying that there's a specific point in the, let's say y is the normal coordinate. There's a specific point where y, the second derivative of y is zero. That's what Riley said. And at the same time, the multiplication of the first derivative and the velocity itself is less than zero. Okay, so he added all the conditions, which is an essential and mistake and an enough condition to have an instability in an inviscid flow. Okay, these results they are for perturbations of 2D, which are superimposed on inviscid flow. Is stable. Ellingson and Palm, which I talked to you at the beginning, it said it is based on an explanation from Ellingson and Palm, showed first that 3D perturbations may lead to a different kind of instability, one that is not even connected to an inflection point. So the usual thing to do that is to take the momentum equation, linearize it, superimpose the 3D disturbance, then use the continuity equation and with the continuity equation build the pressure Poisson equation, and then put everything to the vertical momentum. That's how you do it always, okay? I'm not going to develop that, but that's a stability equation that has an eigenvalue. And another definition they use is the vertical vorticity. And they do some kind of special manipulations, mathematical manipulations to get an eigenvalue problem. So what they get is an eigenvalue problems for the vertical velocity, or the velocity vector if you'd like in 3D. Okay, you can take them from the continuity equations, the other, W and U or whatever. So what they get is two equations, one for the vertical velocity, one for the vertical vorticity, okay, which perfectly describe the evolution of a 3D disturbance in time space. Okay, you can get the problem is a temporal approach. The system is homogeneous, it's linear, It can show that you can go from the, because of that, you can go to, because it's temporal and it's linear, you can go to the wave number plane and look at the behavior of specific Fourier modes. Okay? So what you get is essentially an eigenvalue which describes from an initial boundary problem. You can find the vertical velocity and the eigenvalues for the vertical vorticity. When you decide, now we were talking till now, I said inviscid, I still didn't say viscid flow. We usually are not very interested in viscid flow. I mean, it's only when you want to calculate lift on airplanes. When the flow when the flow has viscosity, the equation for the vertical velocity becomes like a Rayleigh equation dependent on time. This means that for a 2D disturbance, the solution is completely determined by the vertical velocity, because you can get the velocity in the longitudinal direction by the continuity equation. 2D.
So is it not dependent on time in 2D?
It is, yeah, exactly. It is a temporal, but it is a temporal. We have just spoken about the vertical velocity. We still have the vertical vorticity, which is very important. Okay.
Mm-hmm.
So we have eigenvalues. We have an alpha, which describes the growth, and perhaps beta, which also describes the growth for the other component of the eigenvalue problems. We see that if one of them specifically is 0, then the disturbance is 3D, and we have to take account also at the vertical vorticity equation. In the inviscid case, you can just simply do an integration to the vorticity equation, and you get, and I'm going to show you, you get some kind of, I'm going to show you this, even though it's in Hebrew, it doesn't mind, because it's, you see the screen?
Yeah.
Can you share? Did I share? Okay.
Yes, we can see it.
Okay, so as I told you, you get these two eigenvalue problems, okay, for when you solve an initial problem, you can find the rest of the velocity components from the continuity equation, and when, okay, let's see, you see the equations, everything is clear. You have an alpha, you have a beta. That's what we have here. And these are going to play a big role. It was found by Ellingson and Pound, and when beta is 0, then the disturbance is 3D, and you have to also take in account the vertical vorticity. In our inviscid case, we can simply do an integration. We get two objects here. One of them is clearly a modal part, and it's damped. This is simply the advection of the vertical vorticity. When it is superimposed on the basic flow. The second one describes the phenomena that I'm going to talk about, which is the creation of a longitudinal perturbative velocity by an effect called a lift-off effect. When there is basic shear, okay? How does it? How? Let me share back the screen, and then I'll show you again. Just don't want to waste Hebrew stuff that you will not understand. Okay, if we have Fourier mode with alpha equals 0, as you see here, we can let's put alpha equals 0 for this Fourier mode, and you can see something really interesting, really simple. So let's share it again. You can see something really simple here, which means that we have a vorticity, a constant one, and then what do we have here? It's not an exponential growth. It's an algebraic growth. Okay? That's very interesting. Okay? That's the algebraic growth from Ellingson and R. So what is the lift-up effect? And I'm going to give you two descriptions of the lift-up effect, and it's the most important effect. This effect rules most of the mechanism that we know except Thurm-Munch lifting waves. Okay? The lift-up effects happens when we take parcels of fluid which holds their longitudinal momentum. I mean, if you didn't learn what I said, it's the velocity in the longitudinal direction. And when they go up in the direction of the shear, they cause longitudinal perturbations because of the shear. Another easier, much more intuitive description is that disturbance in the form of longitudinal vorticity takes flow with high velocity away from the wall and moves it. It's vorticity, okay? Longitudinal vorticity, and moves it to a place where the velocity is low. Okay? And at the same time takes fluid where velocity, this same longitudinal vorticity takes a fluid with a really low speed from near the wall and lifts it to a place where the velocity is large. What we get when we want to look at the effect is something like this. We take an initial state with shear and we move it to another place, that's what causes the streaks. The streaks that we have in the as part of the transition mechanism. So the transition mechanism itself, turbulent flow, is very chaotic. I mean, you can describe, I mean, with the DNS, I can see here there's a hairpin vortex, there's a lambda vortex, there's a this, there's a that, but it's a very simple geometry. The transition mechanism, especially the Thulmian-Schlichting one, is very clear. I mean, you get the low intensity disturbance, it goes inside the boundary layer, it disturbs the flow a little bit, it creates streaks, the strings get elongated due to the lift-up effect, and then you get turbulent spots when they get disconnected. So that's how basically it works. Okay, so let's talk about some flows. Okay, we always talk about we spoke about solving the eigenvalue problems. We were doing modal analysis. Okay, we take an infinitesimal disturbance, we superimpose it on some manipulated equations, and if we have we find branches where the flow gets destabilized, where the most susceptible eigenvalue leads to the most growth. And we get the model. Model means it's important that you understand what model means. Okay, model means that it's all linearized. Okay, nothing is non-linearized. Okay, and all the eigenvectors are perpendicular. Okay, because they form an orthogonal basis, an orthonormal basis. You remember that from Algebra 1? Yeah. So when we look at Poisson flow, plain Poisson flow, let's say even, what we see is that it has no inflection point. And we're talking about non-model spectral analysis without viscous effects, okay? So it doesn't have an inflection point, which means clearly that plain Poisson flow never turns turbulent. And this is, of course, bullshit. I mean, according to the Riley criterion for inflection point as an essential rule for instability for this inviscid flow.
Inviscid, yeah.
Inviscid, yeah. We have to assume that somehow the vorticity has a part which is destabilizing. This actually against intuition. I mean, this unstable mode, this Thulmian-Schlichting mode found by Orr-Sommerfeld, the 5772 flow is due to vorticity. I mean, so now we have Coet, pipe, and Blau's flow. These are only the flows that were investigated. Pipe flow has the same branches like plain Poisson. They look the same, like 3 branches. If the model frequency cuts any branch, then it can become unstable. Both spectrums in pipe flow and Coet flow seem to be stable to any Reynolds in the model sense. Okay? That's how it seems to be. It seems to be stable in the model sense. So it's not a model instability that makes a pipe flow unstable. The Blausius boundary layer, the flat boundary layer, it's a little different. It has a turbulent Schlichting mode, of course, and you can use that. Okay, so what we get here is we've shown you a second ago this normal vorticity, which has a mode, which has a growth, which is an algebraic growth. Okay, it's not a modal exponential growth. So all the modes, all the eigenvalues are damped. I mean, they get damped. If we check them, nothing happens. But turbulence inherently combine 3D, very complicated flow feature, while laminar flow you can describe by many cases with a 2D flow. So when we study this kind of flow, especially this transient flow, the viscous counterpart, we must take 3D as an essential part, because the 2D investigation of modal growth left of a model, we can call it, they take the whole equation and call it an operator. This linear operator led us to no growth. Okay? So what it led to is an investigation of what is called a secondary instability, where we can start to imagine superimposing a 3D instability, okay, onto the waves with a final amplitude. It's final. It's not infinitesimal anymore. Otherwise, we get again the modal approach and nothing happens. And what's funny that so we take this 3D disturbance and we superimpose it on a 2D flow because it's still laminar. And but this 3D instability is not infinitesimal. This is important. It is very small. It might be very, very small, but not infinitesimal. Otherwise, we get only modal growth. Okay? That's very important. So what we get when we take this 3D instability for disturbances which are somewhat oblique, meaning the vorticity has some obliqueness. It has a part which is in one direction and another in a different direction. And this is the big Dan Henningsen KTH finding. And the wave number that we take is usually the least unstable mode of the Orr-Sommerfeld. It's still unstable. It's still stable. Okay, it's still stable. It's still damping. It damps. If I let it go on time, it damps. It doesn't grow. That's what we said. That's what we're doing. That's why we are doing what we're doing now. So if we take this oblique disturbance and the modal growth, which we found as the eigenvalue with the biggest modal growth, then this 3D velocity, longitudinal velocity, is growing fast, very fast, with this mechanism I explained with the lift up effect. So this mechanism of imposing a 3D, but final but very small, with which can keep its longitudinal velocity, remember that, and join the lift-up effect, can create what we call streaks. Okay? And it is very interesting because we can actually describe it as they are actually local in time space. They are also 3D. We can actually describe this by a solution to an initial problems. If we develop this solution with the composition of the modes of this Orr-Sommerfeld and Squire equations with the amplitude contact of each mode, it can give us a connection between Orr-Sommerfeld modes and Squire modes to the effect of the lift-up. And it shows us the creation of the streaks. Streaks are the most essential part of transition. So what we are going to do now is try to explain verbally how this transient growth, because it's not a modal growth. I showed you this algebraic growth. How this transient growth happens. If we assume that the normal vorticity, the one we have in one of the equations, is 0 at the beginning, meaning we are solving an initial boundary problem, and this eta 0 times 0 is 0. It's easy to see that a mode of Orr-Sommerfeld excites some mode of the Squire equation. This excitation has to be determined such that the Squire excited modes cancel the vorticity, which is part of the private solution at t equals 0, because we said the vorticity is 0. When time continues, these Squire modes and the vorticity which we saw of the algebraic growth are going in different paces, and they have different time. They have different rate of growth or damping. Let's say different growth, and they will not cancel each other besides in this initial moment. Okay. So this cancellation of the eta 0 in the initial conditions in 0 happens only in the initial condition. And the total normal vorticity grows. It grows for some time. How much time? We can show that for Reynolds of 3000, we get maybe we'll take a sense that is even more amazing. So that's when we got into this world of taking some kind of 3D disturbances and imposing them. One of them is called the oblique wave mechanism by Dan Henningsen. One of them, I mean, they take different mechanism and impose them, always use the lift-up effect. They can show by simulation that the normal velocity is evolving like a wave packet and is damped according to the initial condition, while the vertical vorticity is equivalent to the vertical velocity at t equals 0, but then grows drastically. This drastic growth is the lift up effect, and this is conducted by simulation. But there is some problems here, and then you want to continue now, or you want to stop? You say it's your decision.
Continue. Why stop?
Continue. It's going to be 15 minutes of some stuff which is really interesting. There has been a big fight over this. Big fight between a guy, professor named Walleffe, and Dan Henningsen. They used big fight means correspondence, and review correspondence, stuff like that. And as I told you at the beginning of the conversation, the reason I'm a free spirit. I like 2 hours of meditation, not fighting with someone.
No politics.
Yeah, and the issue was non-normality versus, so what we have here is this transient growth, which is see later. It's not because of modal eigenvalues. It's because of modal orthogonal eigenvectors. It's because a very non-normal operator. It can be seen that a non-normal operator doesn't have to be normal, okay, to be a basis, can give this transient growth. But then a big question rose. It's true, we have the Reynolds Orr, what I spoke about at the beginning. The only, if we take base flow and they add disturbance, both of them, stand to the Navier-Stokes equation. We do scalaric multiplication with the perturbic. We get the energy, in essence, okay? And we see that the only mode of growth possible is algebraic growth. Okay?
Okay, so no damping.
So not about not damping, but there is something else that happens. While the vorticity grows and grows in a high, if I decide that the disturbance is local and I use what I use, and since we're dealing with fluids that the base flow is not affected from the we say like we superimpose the disturbance on the base flow. We can see that the nonlinear, we said that before, the nonlinear stuff drops, and okay, the rate of growth is not dependable on the amplitude of the initial disturbance. Okay? In other words, the rate of growth of final amplitude is given every moment. It can be found from an infinitesimal perturbation with the same shape. That's essentially an NSE conclusion. That's what Walleffe said. He took this and he said that maybe what we thought to be a transient growth of non-normal mode that we showed you, maybe it is caused by interaction with linear mechanism and non-linear mechanism. Well, the non-linear mechanism cannot cause growth. We saw that in the Reynolds Orr sentence about the energy. but they what can nonlinearity do? It can redistribute energy between and this is very interesting.
Wow.
So we get a question that means the linear part gets the rate of growth, which is positive but it's a transient growth. It's for some kind of time. Then the nonlinear part takes the energy from one direction, and it doesn't create or destruct the energy. And it's always orthogonal to the motion. It's conservative. But if we check the growth of the amplitude for a certain time, it's much larger in the nonlinear case than in the linear case. This effect Walleffe called bootstrapping. He said, imagine that in t equals 0, the vector has an amplitude of epsilon. And it excites this growth for the linear problem, like we said, the transient growth in the vertical vorticity. Then after some time of an order of Reynolds, let's say, the solution grows to size of r times epsilon. Because that was the initial, that's the time passed. It's a transient growth, r times epsilon. By a linear mechanism, totally linear. It's a linear mechanism.
That's why it's r times epsilon.
Yeah, because that's the only growth possible by the Reynolds or definition. But it moves to but the nonlinearity, because it is not, it has some amplitude, it's not infinitesimal, but the nonlinear part removes it to a location which doesn't excite any more growth. In the meantime, at the same time, the nonlinear had an effect of taking some of this energy back to the original direction, the one we said had an epsilon, but now with after this time with an amplitude of r epsilon squared, because the nonlinear is squared. So the time is of an order of r, and then r pass, so it's r times r. So the size, the order of magnitude is smaller than if it's smaller than epsilon, then the energy will then be damped. But if the order of magnitude is larger than epsilon, there is more energy and than in the beginning, and we get what is called sustained growth. It is a very important topic. How we sustain turbulence, and it is so interesting that it seems to contradict the Reynolds Orr definition of the only growth to be linear growth. But if we pay attention, we see that the growth in its essence is linear. In the beginning, the nonlinear part doesn't create or regenerates energy, but it redistributes it between modes. Secondly, the phenomena has no connection to nonlinearity, but it has a connection to its quadratic form. Okay? On the other side, the nonlinear mechanism needs to taken into place with canonical flows, like we talked about a minute ago. So now we get to what is called the resolvent of a flow. We say that the resolvent of a flow is an operator who makes a transformation which is essentially an excitation to a flow V by an output U. Okay? So since we can connect the random perturbation through an Fourier analysis with the integral, we get some kind of growth, and this growth is totally, and I'll show you it here. It's totally an eigenvalue problem. You see the screen?
Yeah.
Okay, it's totally an eigenvalue problem thing. When the modes are modal, what we get, I'll leave it here, okay? Because it's very important. It's going to lead to another. I'm going to invent something. It's an invention of mine. When we're talking about modal growth, this we take the operator, we put it, we take the resolvent. It could be only singular when the mode is growing, so it could be only big near the eigenvalue, which is unstable. Okay, very near.
Mm-hmm.
But when we take the non-normal modes, we see an interesting thing. We define something which is called an epsilon pseudo-spectrum, which means for an epsilon, this epsilon that we talked before, which was the growth, and some kind of frequency, which is an eigenvalue. Is an epsilon pseudo eigenvalue if it accommodates this. This is a usual thing for. This could be for normal and non-normal, exactly the same. What we see is that for to our intentions, for operators which are normal, which are orthogonal operators, the set of all the points that are closer than epsilon is always near the least unstable eigenvalue. But what we see for non-normal operators, that the distance could be much bigger.
Mm-hmm.
Okay, now I'll show you here. We share, and you can see the trends and growth. And I want to go especially to forest of hairpins on about CFD. Okay, looks the same, kind of the same. And now we're talking about the bypass transition, these distortions. I recommend reading it, and I'll show you the beautiful picture. But we're really getting here is the Walleffe suggestion of nonlinear interaction and sustained coherent structures. It's very important. I mean, you have a mechanism that allows you to sustain turbulence. Why is it sustained? So that's what Walleffe said. They had a fight between them. And, I was such a fan of Henningsen. I read all his books and all his articles, and And I was so disappointed that you saw, I actually took it and I had to write the thing because it made so much sense. So you can find here the fine-grained mechanism, but the interesting thing that for an operator with a normal operator with normal modes, if I'd like the modal growth, the biggest one, I'll take the highest mode with the highest resonance. The pseudo spectrum exists, but it cannot give larger growth. Operator, like in plane Poisson, you can see that the spectrum starts to cut a lot before 5,772 that Orsag, the late Orsag made. That happens with transient growth. The pseudo spectrum gets inside a lot faster due to this bootstrapping effect.
Yeah.
Due to this redistribution effect. So it's very interesting. So what you can say actually is you can have it in two ways. You can take a base flow, a 2D base flow, superimpose second 3D disturbance, get a disturbed flow, and then solve what is called the Fluke analysis for a new flow. But you can also say that the growth to the original flow is because of a pseudo mode and a bootstrapping effect on the base flow, the base laminar flow. And so this is like something which I don't think you see anywhere, but basically what Fluke analysis does, it takes a distorted flow, and now it's very hard to, and what we have here is simply a bootstrapping effect of a disturbed flow, this distorted flow, and this distorted flow is the epsilon is the pseudo spectrum. It's not the spectrum. It's not the modal spectrum. It's the pseudo spectrum when we know that there is this nonlinear quadratic bootstrapping effect that works in every the interesting thing came there's a lot here, but the interesting thing, we talked about oblique wave, oblicity, that's the title. The most interesting DNS conducted, talking about CFD, was conducted by Wu and Moin, and it took a special approach when local disturbances, it was really an especially amazing DNS, and it actually replicated what we thought we would see from the bootstrapping effect. And it was quite an amazing thing. Okay, so you can take, as I said, you can do, you can, the same way that I talk about the pseudo mode of the initial flow, you can do a secondary instability analysis. You can take the flow, you can do what is called Fluke analysis. That's the principles of secondary instability analysis. You can do it on basic flows in a quasi-steady state. which means that if the growth rate, the secondary growth rate, is higher by far than the time scale of the base flow, then it's quasi-steady state. Okay? This analysis usually was applied on the most unstable model, the Turbine mode, the model one. It adds to the base flow, so it leads from from a wave which is 2D and unstable to a 3D. But the how it does that is will prove that you need the all these stages we talked about. After you apply the Fluke analysis, you would see first of all these the lift-off effect, which takes the fluid from which remains with his momentum in the longitudinal way and takes it up the shear to a faster place near the wall and the opposite, and by that getting transient growth of streaks. Okay, and then the same. But when do so now you ask you'd probably ask, so when do we see this one and when do we see the Turbine one? Actually, it depends on the intensity of the turbulent of the. Yeah. No. It depends on the background turbulent intensity. The larger the turbulent intensity is, the more chance Turbine works for very low turbulence intensity. Otherwise, we get Fluke analysis. I'm going to show you a secondary analysis just for the case of it. I actually wrote that. I'm stupid. Do you see it?
Yes.
Yeah. So yeah. So but the main thing after writing all of this is that we can first we can represent a streak, but it's the Landahl effect, totally the Landahl effect, which is explained by the vertical vorticity taking fluid. Again, I'm repeating longitudinal fluid parcels which hold their momentum and picks it up in the vertical shear to a place where there is less velocity near the wall or more velocity above the wall. Okay, so and basically we can get even a mathematical representation for a streak, but it's not really and that's Fluke analysis. Yeah, this is very interesting. And the last thing I wanted to talk about, and the last thing I'm going to talk about, because I think it's important. On this one, the resolvent I've explained to you.
Yep.
The impact of initial condition I explained with the bootstrapping effect. The epsilon pseudospectrum was explained also. The redistribution, the maximum growth. Okay, so there's an issue with epsilon pseudo spectra to find the optimal growth.
What do you mean by optimal growth?
Okay, so if I take wait, I'll show you it. That's a little bit. I want to show you exactly the numbers because then. Okay, here it is. Okay. We would like to be able to explore what distortion to the base flow maximizes the rate of growth for a mode. For otherwise was modally stable, okay? In the transient growth effect, okay? On the same token, we can look for the minimum norm of moving a little bit away from basic flow. And this by this we get some kind of neutral stability, and it's called a minimal defect that we put on a flow. Now what we do is an optimization process. We develop a sensitivity function which connects the eigenvalues with the changes in the base flow from variational concepts, and we find the minimal defect that creates this growth.
So that's what you mean by optimal growth.
Exactly.
So the minimal defect that causes this growth.
And but what is important to say here. So these are the many ways Modal solution. And I got to the Modal approach. Maybe I'll translate it someday to English. I think many people. So what we said, we want to find the initial disturbance which will lead to the most growth, right? We call this one the optimal disturbance theory. So we look for the maximum. We have growth function. Take some certain time of the disturbance, and we'll check that by an optimization to different initial conditions. They can change. This this procedure of finding the optimal growth includes an optimization for every initial condition, and we need to see that we choose every time the choice of interval can also give different initial condition which maximize the growth. So it's so.
You mean time intervals?
Yeah, okay. Exactly. So this is where it ends. Okay, so another limit which is more relevant for the non-normal operators which is the main issue here, because besides no normal operators, all we have is Thurmian-Schlichting waves, natural, what we call the natural condition. Another important limit, which for non-normal operators, is that of when t goes to 0. The initial growth of the initial growth of this unstable mode is something that we usually would like we usually can find. Okay, so it's the supremum of the what it gives us essentially is the mode, the mode which will give us the biggest transient growth. So this is also important. So we're not taking now the most susceptible mode, but we're taking another one which will give me the greatest supremum for the growth itself. So that's the other issue. So we'll conclude because it always took me 2 hours. Somehow 2 hours is the ideal time. I'll conclude with showing you the fine grain, the streaks, or the Klebanov distortions, which are the streaks. The subharmonic, the subharmonic transition process, but both of them are essentially connected to the both the sheltering of the boundary layer of we get the turbulent density in many frequencies, okay, modal frequencies. Some of them are shielded, some of them are unshielded. Some of them go inside, some of them don't go inside. So the two most noteworthy instabilities we get is the what we call an instability, high frequency perturbation, or done by the boundary layer, shear layer. And the two of the most important instabilities we have in transient growth are called the continuous mode, which is more prevalent. We see it usually in boundary layers, and the varicose mode. And it should be noted that the boundary layer can still be considered to be laminar at this time. Turbulent distortion, Klebanov distortions, the streaks, the usual lift-up effect, and the distortions they grow downstream, and when we have this effect of bootstrapping, they get stretched. I mean, elongated. The streaks get elongated, and we get turbulent spots, which was one of the first. These turbulent spots coalesce further downstream, and then we finally get turbulent flow. Besides that, we have the very uninteresting turbulent spots we get from the okay, this fine-grained explanation is exactly the bootstrapping things I explained to you before, and the sustained growth because of the redistribution of energy and the non-growth, but the returning back of the flow to the same direction, but with quadratic growth. I'll show you now. What I'm showing you now is Schlotter's and Henningsen's turbulent boundary layer. I'll give you a book. We'll talk about it afterwards.
Okay.
We'll talk about it afterwards. I don't want to, it's kind of illegal. So, Peter Schlatter became a very renowned professor now. It's beautiful. It's absolutely beautiful. What you see here is, I think it's a larger dissimulation. It might as well look like a DNS. It's
Incredible.
you see hairpin vortices, I think.
Yeah.
You see them. It's very beautiful. You see the elongated streaks before that. You see them?
Yes.
It's pretty amazing. You see the Reynolds is going further up and 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 up. This thing is so small by size and takes so much of computer resources you wouldn't imagine.
It's probably a couple days of simulations right there.
I find Schlotter's dissertation, which I'm going to send to you. You can download it if you want, but I'll send it to you. If just all of you email me after I'll send you a lot of material. Okay.
Perfect.
Email me directly after the Alexandro.
Sure.
Poor Alessandro. You got left outside for a long time. And I'll send to you. If you really want to get remembered with everything I said, you can read about and this is another simulation, but I think it's the same one. I don't think it's. This is the DNS I showed you that Wu and Pavis Moin. Pavis Moin is in charge of the Turbulent Center in Stanford, for those of you who don't know. He's Iranian, but and it is called the ZPGFPBL. The zero pressure gradient flat plate boundary layer. They actually use this maybe. So you get a forest of hairpins, beautiful DNS, the first DNS in this level. Since then, they did a lot of work. They even had a transient from which covered high Reynolds and from both spatially and transiently, and you can follow their work. Many of it is on this subject, and I think if you want to get remembered a little bit about what I said, it will make you remember the stuff we said before. So the varicose mode, which is the Wallman normal mode, which is more like this violent inviscid instability that I try to look for in a pipe. But I while doing that in a thesis, I started to believe that like I'm investing, like you're a professor and you're investigating something for a lifetime, and it's wrong. So that's how I felt. I felt I'm doing something which didn't make sense to me. I used to walk with the dog, and the poor dog was already he wanted to drink so bad, and I'm still walking, thinking about the pseudo spectra of the stability equations, and I was really crazy at the time. Okay, so I call it velocity streaks. The velocity streaks I call pseudo modes of Orr-Sommerfeld Squire, or otherwise. Well, you can take this and you can remember all of what I said. I just get into it a lot in a lot fine-grained. It's a hard subject. I'm sorry, it's
No,
a
but
very
it's
hard
very
subject.
interesting, you know.
It's the hardest subject, I think. It's a lot harder than problems of multi-phase, which simply we don't know enough about the physics. Here, it's really something that happens all the time, but we avoid it all the time. So I see he's not here anymore. But all of you send me, except you, Rajat, you don't need to send me anything. Because send you anyway. And a lot of material, very important material, including the Schlotter's thesis, the Dan Henningsen and Schmidt book, which talks about all this stuff, and preferably also what we didn't talk about enough is the LCTM model. If you'd like to use it for runs calculation, I would like you to have a full explanation of what is actually happening there. And there's an amazing explanation. You're going to know exactly what the transition model means, what happened there, and why does it cover all the mechanisms.
Sounds good.
But only for onset and of course, it doesn't have the fine-grained resolution. Okay?
Okay.
So it was very. I'm always stunned when people take the time and a lot of time to listen to me.
No, thank you for doing this. This is amazing.
I appreciate it very much, wholeheartedly.
So you are a professor, see?
I'm a free spirit. I mean,
Yeah, there you go.
know,
Free spirit.
Just so you know what I'm doing in my life. I don't have a day job. Mm-hmm. I have my blog, which the deal with the new company is that I actually advertise them. The blog is there anyway, so you might see in the end. I think you see MSI.
Yes, MSI.
Yeah. So and I'm very well connected on LinkedIn. Mm-hmm. Probably you know that.
Yes.
And so I can get them leads. So I get money for leads, money for that. Mm-hmm. I give Zoom. I help doctorants. I have a doctoral student from Ben Gurion University. I now help with botanic dissertation to do the fluent stuff. It's good for me because since I left Tenza, I haven't had fluent. I'm not stating softwares. I don't want to get in trouble. Mm-hmm. So I'm opening the TeamViewer and I have a chance again to play with my lovely software. So I'll send you a lot of material. I'll send you also another very good book. I can't stop recommending it. Do you see the screen? The screen changes.
Yes. Yeah.
This is this book.
Understanding Aerodynamics by Doug McLean. Okay.
Doug McLean is an experimentalist.
Look at that picture.
It's it's amazing. He's an experimentalist from Boeing. He's a good friend of Philip Spallard, but he's not a CFD guy. Mm-hmm. What's so special about the book is that it's a phenomenology book. It has none whatsoever equations.
So it just speaks about the physics of the
just about the physics from kinematics,
that's very nice.
Streamlines. it's the best book by far I read
That's
about.
very nice. So you can actually imagine the phenomenon in your head by how he explains.
Yeah, no. He also talks about how turbulence happens exactly.
Cool. That's
How
very cool.
eddy viscosity mechanism happens. How it's an amazing book. I think it's the best book I read. Even though I read Schlichtings and all the rest of it. So David D. Wilcox, I think you asked for it.
Yeah, there's John D. Anderson
So
right there.
Anderson, I don't really.
You don't like?
I don't like. He has many mistakes in it. To my soul. I mean, it has many. You can watch the Lorna Barba 32 lectures, and that will cover you the part of the Anderson book about discretizations and stuff. And it's better to read Doug McLean's.
Perfect.
Because his is perfect. Okay, so this one you'll get. If you want this one, you can get it. This one you'll get, and you will get this one. You get others also, but you'll get the one from Henningsen and Schmidt. Okay.
Okay. Thank you so much, Tomer. Really, this is great.
And some other stuff, I think, which is important for you to be efficient, because you don't have like the time I'm overspending for you now. So have a good time, guys. Keep in touch.
Thank you.
Put some likes on my posts from time to time. And I enjoyed you. I'm really thankful for you being here. Have a wonderful day and a wonderful life.
Thank you, Tomer.